The name of this video is Ohm Integral. In a previous video, we examined already Ohm's law in local form, which connect, of course, the electric field E and the vector density J. In this case, we want to find the integral form, which is the well-known potential equal resistance times current. So how do we proceed to find this equation? Let us consider a conductor, and we just take a section of this conductor. Okay, it's like a big wire. This is one end of this conductor, so it's a conducting plate, if you want. And for example, this wire can have any shape you want, like this. This is the other plate of this section of conductor. So the top plate, we call it, as always, 1. This is the positive plate, this is the positively charged plate. Whereas negatively charged, we call it 2, as always. It's down here. We call it the negatively charged plate. Now, in order to solve this problem, we want to use quasi-simpler, quasi-filiform flux tubes. We could do the same with filiform flux tubes, in which case, instead of sums, we need to substitute the sums with integrals, but I prefer to use quasi-filiform flux tubes. So you can consider each of these quasi-filiform flux tube as a spaghetto, as we've seen before. So basically, this conductor is a bunch of spaghetti. These spaghetti, however, they're not as simple as those we've seen in a previous video. I'm generalizing the concept of spaghetto now to make it with a non-uniform cross-sectional area. So let's look at our spaghetti a little bit more in detail. So one of these quasi-filiform flux tubes or non-uniform spaghetti will be characterized by a longitudinal axis, let's call it gamma. For example, here, we call it gamma. This gamma goes from 1 to 2. There will be many of these gammas. There will be capital N of these gammas with an index k when I consider one of them. And this, we will call it the origin, as we will see in a minute. So then, let us consider one of these spaghetti around this axis. Like this. Okay, so to understand a little bit better what's going on here, let's consider another spaghetti next to it, just to give you some three-dimensionality. Could be something like this. So here, if I take a cross-sectional area, it looks like this. And here, a cross-sectional area looks like that. Okay? So this is a 3D version. Here, I will only sketch the 2D version for simplicity. Okay, so if I consider this object here, now we can define a curvilinear coordinate which has origin here in O. And for example, if I pick this point here, this point will be the distance L, small l, from the origin. And so here I can take a cross-sectional area of this type. So for example, in this case, the normal unit vector of this cross-sectional area is this. This we call it N, which in general depends on the curvilinear coordinates L, because of course it varies along this axis gamma 1 to k. So this area, we call it delta A k at L. So this is this area here, delta A k at L. So these are quasi-filiform therefore delta A instead of dA. Flux tubes. We will use all the properties of quasi-filiform flux tubes to solve this problem here. Okay, for example, if I'm considering an oriented area, the oriented area will be N function of L times delta A k function of L. If I'm considering an infinitesimal element of length dl on this gamma 1 to k line, this will be t, which is also a function of L, times dl. As it turns out, n at each point L is exactly the same as t at each point L. We just change the notation depending whether we are using an oriented area or an oriented infinitesimal element, but they're actually the same. So n and t are the same. Okay, just conventions. In this case, they are the same. We've seen already this in a previous video somehow. Okay, but now we are formalizing a little bit more. So, with this in mind, we now want to use the fact that these are quasi-filiform flux tubes. So what is the implication of having quasi-filiform flux tube? Well, if I have a current density J at point L, or an electric field E at point L, similarly, I can have a resistivity R or a conductivity S. All these quantities, and I leave some space here, you will see in a minute why, they have to be the same. Okay, be careful when I mean the same. Each of them has to be the same, so they are all separate quantities. That is, J at point L has to be the same at each point on this area, which is very small, quasi-filiform delta AKL. So let me be more specific, just to make sure we are on the same page with this. So if this one is J at L, because of the quasi-filiform condition, this JL has to be the same at each point on this small area delta AKL. Similarly, EL, and similarly the resistivity and conductivity. Now, the reason why I left some space here in RNS, because we will consider, for this problem, instead of isotropic, linear, and homogeneous ILH conductors, we are going to consider isotropic, linear, and non-homogeneous NH conductors. When a conductor is non-homogeneous, if you look at the previous video, this means that the resistivity is function of position L, as well as the conductivity, which is the opposite of the resistivity. Good. Now, with all these definitions in mind, we want to compute the flux of J across delta AKL. And we want to use the fact that these are flux tubes. So, if I compute the flux on a flux tube, and of course I'm considering, as always, steady currents, what do you think happens? Well, clearly, the flux is going to be J at L, dotted with N at L, times delta AK at L. This quantity, note that J and N or L are parallel to each other. And N and T are the same, not L, I mean T. So J is parallel to N, which is the same as T. So J dot N obviously just gives me J at position L, this dot product. Multiply times the area, delta AKL, which again can vary. Remember the Euler approach here and the water from a tap. So we know that in steady conditions, even though these cross-sectional areas are different, the flux has to be the same across each cross-sectional area, which means no matter what, so even if I choose different values of L, yet this flux, because of steady conditions, has to be equal to a constant, which I call IK, and this constant is a current, a DC current. Note that sometimes in the past we were using this symbol for a current, and now I changed it to this symbol, which is more common for DC currents, which are steady currents. Okay, so that's what we get here. And in fact, we want to invert it immediately, not to forget to do so. And this allows us to find the J at L in magnitude, which is given by IK divided by delta A K at L. So now we use the fact that we have a quasi-filiform and a flux tube. The next thing we want to do is we want to use the definition of work. So by the definition of work, we know that the line integral on gamma 1 to K of E, the electric field at L, dot, that is at this point, N at L, which is the same as TDL. So this one, note that typically we write as TDL, but we can confuse them now because actually they are the same. DL, so this quantity is equal to the potential difference delta V between 1 and 2 a k. And this quantity, for simplicity, let's just call it Vk. Actually, let's put k in the denominator, even easier, as a not in the denominator, sorry, as a subscript. Obviously, that's what I meant. Good. All right, for simplicity of notation. Good. So now that we have the potential difference, we can use Ohm's law. So we know that this, from Ohm's law, it's equal to the integral on gamma 1 to k. So I'm using Ohm's law. So E is equal to R, which is function of L, the resistivity, local form, times J, which is function of L, and we know it from this relationship here, dotted, this we can say either T or L. Now, since I'm using J, let's use T, and L, the L. Now, this quantity here, we can rewrite it as J of L, we can substitute it here, so it's Ik, but Ik is a constant, so I can take it outside. So Ik is outside the sign of integral because it's a constant, okay, for each cross-sectional area, doesn't matter. And so divided by delta AKL, and we know that J and T have the same direction, so this dot product just gets rid of this T if you want. And so here we get the line integral on gamma 1 to k of RL, which remains inside the sign of integral because it's a function of L in general, non-homogeneous conductors. And this obviously, now we need to substitute JL in amplitude, which is IK, we already substituted that. And so it's going to be DL, from this DL here, divided by delta AK of L. And all these quantities must remain within the sign of integral because they're all function of L. This, by definition, we call it the resistance RK of the kth spaghetti here, spaghetto, of the kth flux tube. Okay, so remember we need to sum to get the overall current in a minute. And so this is nothing but IK times RK. Now, from the fact that this plate 1 is the same conductor and this plate is the same conductor, each of these plates must be at the same electrostatic potential. That is, Vk, actually we can call it simply V. In fact, this is a typical property of parallel circuits, which is what basically we are analyzing here. You will see this in circuit theory courses eventually, maybe one day. And so this is Vk is equal to V, and this V is equal to IK RK. Therefore, we can invert it to find that Ik is equal to V over Rk. Okay, with this in mind, now, the other condition for parallel is that we need to sum up all these spaghetti together, or these flux tubes. That is, the total current I is going to be nothing but the sum over K, over possible flux tubes of Ik, and note that again, if I were to use filiform flux tubes, this would be an integral over dA, but it's easier for me to explain like this, in my opinion. And so now we substitute it, and we obtain that V is a constant, so we can take it outside the sign of sum. Sum over K, whatever is left of Ik, which is 1 over Rk. So this is the inverse of something which has units of ohms, and so this quantity we call it the conductance. So this is G, the conductance, times V, where by definition this is our conductance, the inverse of the resistance for the kth flux tube. Okay, but since the sum is already the total G. And so if you want, you can invert this relationship and you can write V equal 1 over G, that is R, times I. And this is the integral form of the well-known Ohm's law. In a similar fashion, you should be able also to derive the integral form of Joule's law. And I will actually do that as an exercise. So let me write down here. In Piazza, try to do Joule's law in integral form, following the same kind of argument as I've done here. And so to recapitulate this video here, we derive Ohm's law in integral form. To do so, we took a segment of a conductor of some length. We split it up into many spaghetti, that is many quasi-filiform flux tubes. Each flux tube is very generic in this case. I wanted to make it more complicated than the previous videos. So we have a cross-sectional area which varies according to this curvilinear coordinates L, as you can see here. And so we define a bunch of things here. particularly the fact that this is quasi-filiform, so field E or current density J are the same at each point on these cross-sectional areas. The fact that this is a flux tube means that the flux through any of these areas, no matter if I take this area which is small, or this area which is big, or whatever, this area which is even smaller, the flux, remember the water from a tap, has to be constant in certain conditions. So we obtain this equation here, which allows us to find out J. Then we write down the work to move a particle from here to here, along this gamma 1 to k. And we use Ohm's law, so we can use this relationship up here, this function. And so we do that, and we find the Ohm's law in integral form for one flux tube. But now in parallel conditions, because these plates and these plates are at the same potential, we can sum them up in this fashion, obtaining the overall Ohm's law. That's it.